So in this video, we're going to be talking about approximating areas with Riemann sums. We're going to go ahead and, just since this is reviewed, do this all in one day. But I'm going to split it into a couple of videos here. So your essential question is, how do you approximate the area under the curve using geometric and numeric methods? And then we split it into three I can statements, so that way you can kind of narrow down when you're assessing yourself, making sure you understand all three of these things. So I can understand the area, I can find the area under the curve using a left or right rectangular approximation. I can find the area under the curve using a midpoint approximation. And I can find the area under the curve using a trapezoidal approximation. So yesterday we ended with this topic, or this question: a particle q moves along a straight path. The graph of the velocity of the particle q, v sub q of t, at time t is shown at the left. How would one go about finding the total distance traveled from t equals 0 to t equals 2? And yesterday we had some really nice geometric shapes in there. But today it's a curve. So we know we've got to get the area underneath, and we could try drawing some shapes in there. Some of you told me that yesterday. So we're going to use some of our rectangular, our Riemann sums to do this. So although there are many possible techniques to approximate the area under the curve, we will use rectangles, or what we call Riemann sums or trapezoids, in AP Calculus. So it says, approximate the area in the curve using rectangles. When using rectangles to approximate the area in the curve, we must decide a few things in advance. How many rectangles we use, so we're going to call that subintervals, and how we will determine the height of each rectangle. So our options will be the left endpoint, the midpoint, or the right endpoint. So this time we're going to use a left Riemann sum with one subinterval to approximate the area under the curve of that function from 0 to 2. So if I'm going to use a left, I know I start my rectangle height at the left, and I draw my rectangle. So that's the area that I'm going to find. So I would go ahead and find the area equals. So I could put it into this formula. That's totally fine. I can also just grab it off of the picture this time. So I know that my area equals my base of my rectangle 2 times the height of my rectangle 1, which is just going to be, actually I should put it into the function. Let me put it into the function for you. Okay, so the base we know is 2 wide. The height of the function, I would take this 0 here, because we started with our height, our x value of 0 to calculate our height, and I put it into this function. So 0.5 times 0 squared plus 1. Well, that's going to make this 0, so my answer there would be 2 times 1, which is just 2. We are now going to use a left Riemann sum with two subintervals that are equal. So I'm going to split it into two subintervals this time. I'm still coming at it from the left, so I'm going to draw my first rectangle here. And then I'm going to draw my second rectangle here. Okay. And we're going to find the area of each one of those rectangles. So my overall total area equals the base, which is 1 wide, and then I put it into here using the left value. So I'm using the 0. So 0.5 times 0 squared plus 1. That gets me my first rectangle. My second rectangle, the base is still 1. The height, though, I'm using this value here, the 1, in order to calculate my height. So 0.5 times 1 squared plus 1. All right. So we know that this is going to be 0. That's 1. So I have 1 times 1. This is still going to be 1. I'm going to have 1 squared, which is 1, times 0.5 is 0.5, plus 1 would be 1.5, or 1/2. Oh, sorry, 1.5. So this is 2. So it's not 2. It's too early in the morning. This is 1. And then that would be 1.5, which is 3/2. So I'm going to rewrite that as 2 halves. So my final answer is the area under the curve, or the estimate of the area of the curve, is 5 halves. We're going to use the right Riemann sum now with 2 equal subintervals. So if I'm coming at it from the right, I like to come at it from the right side completely. So I start with my rightmost x value, which is this 2. So I started here. And then I'm going to come at it from the next rightmost x value. So this is the x value that I'm going to use in the second part, is 1. All right, and then I have area equals, and I literally write it backwards, okay? So my distance in between, or my base of my rectangle, is 1. And I'm going to plug into this function. So 0.5 times 2 squared plus 1. And then this here, the distance in between, is still 1. And then I have the 0.5 times 1 squared plus 1. Well, we know from the previous problem that this part here turned out to be 3 halves, right? So I could just write 3 halves for that. This part here, we're going to have to do a little bit more calculating. So I know I've got 1 times, so I don't need to mess with that. So 1/2 times 4, which is 2 squared plus 1, which equals 3 halves plus, that's going to go into there twice. Although, is that really the best course? We shouldn't have probably done that, but it's okay. We'll try it. So that means I've got 2 times 1 is 2 plus 1 is 3. I've got to turn it into halves though, so 6 halves, which would be 9 halves for my area under the curve. So what do you think will happen with our approximated area if we were to use more rectangles? So the more rectangles you use, the better your area approximation is. So if you use more rectangles, your approximation will be more accurate.